Resultant of two forces. The net effect of the forces is single force, which is called resultant of the forces. Or a single that gives combined effect of forces is called resultant force. Explanation. If two forces F1 and F2 are acting on a body at a straight line but in opposite direction and body remains at rest or in equilibrium, then we say that F1 and F2 are equal in magnitude but opposite in direction. F1 equals F2 if two forces F1 and F2 are acting on a body at a straight line but in opposite direction and body moves in the direction of any of them which is greater than the other. Net force is calculated as then we say that F1 and F2 are equal in magnitude but opposite in direction. F2, F1 net force. F1, F2 net force. Body will move in the direction of greater force. Resultant of two forces acting at an angle. If two forces are acting on an object making a certain angle, in this case force can be represented in magnitude and direction by two adjacent sides of a parallelogram IM. The resultant force Fr is a vector represented by the diagonal from the point of intersection. This is called the parallelogram of forces. As PR is diagonal of IM PQR is so the resultant is diagonal and the IM is called IM of force F1 and F2. By head-to-tail rule, we can draw force F1 from the terminal point of force F2. To get the resultant Fr, we draw a vector from the initial point of force F2 to the terminal point of the force F1. This is the same force as obtained from IM of force. Equilibrium. When the resultant of all the forces acting on a body comes to zero, the body is said to be in the state of equilibrium. Or the body is said to be in the state of equilibrium if leftward forces are equal to the rightward forces and upward forces are equal to downward forces. Example. 1. A book lying on the table. 2. A train moving in a straight line with a constant velocity. 3. A body hanging at rest from the ceiling by a vertical string. 4. A paratrooper moving down with uniform velocity after opening his parachute. Types of equilibrium. There are two of equilibrium: 1. Static equilibrium, 2. Dynamic equilibrium. Static equilibrium. If some forces are acting on a body vertical or horizontally and the body maintains its state of rest, then it is called static equilibrium. Example. 1. A book lying on the table. 2. A body hanging at rest from the ceiling by a vertical string. Dynamic equilibrium. If some forces are acting on a body vertical or horizontally and the body maintains its state of motion. Then it is called dynamic equilibrium. Example. 1. Train moving with uniform velocity. 2. A paratrooper falling down with uniform velocity. First condition of equilibrium. Statement. The body is said to be in the state of equilibrium if the resultant of all forces acting on a body is equal to zero. In other words, the algebraic sum of all the forces acting along the x-axis should be zero, and the algebraic sum of all the forces acting along y-axis should be zero when first condition of equilibrium is satisfied. The body is in translational equilibrium and there is no linear acceleration. Second condition of equilibrium. Statement. The body is said to be in the state of equilibrium if the sum of all the torques or moments acting on the body must be zero torque or moment of a force. Definition. It is the turning effect of force about the axis of rotation. Torque or moment may rotate a body in clockwise or anti-clockwise direction. Types of torque. Negative torque. The clockwise torque is called negative torque. Positive torque. The anti-clockwise torque is called positive torque. It is denoted by the Greek letter formula. Torque equals force x moment arm unit. The unit of torque is Nm. Nature. It is a vector quantity. Moment arm. Definition. The perpendicular distance between the line of the force and the axis of rotation is called the moment arm. Notation. It is denoted by d unit. Its SI unit is m nature. It is a vector quantity. Factors on which torque depends. Torque depends upon two factors: 1. Magnitude of the applied force, 2. The moment arm. Torque increases with the increase of force. Torque is directly proportional to the applied force. Torque is directly proportional to the moment arm. Principle of moment. Statement. According to the principle of moment, if a system is equilibrium under influence of some torque, then the sum of clockwise torque is equal to the sum of anti-clockwise torque. Mathematically, in the equilibrium position, clockwise torque equals anti-clockwise torque. States of equilibrium. There are three states of equilibrium. They are the following. Stable equilibrium. A body is said to be in stable equilibrium if it returns to its original position when tilted a little. Or the center of gravity of a body rises with a jerk is called stable equilibrium. Example: 1 book on a table, 2 chair on flat ground, 3 table on a floor, 4 a standing car on a smooth road. Unstable equilibrium. Definition: a body is said to be in unstable equilibrium if it moves further away from its original position when tilted a little. Or the CG of a body lowered with a slight move, the equilibrium of that body is called unstable equilibrium. Example: 1 stick standing vertically on the tip of a figure, 2 standing pencil on the table, 3 an acrobat walking on the rope. Neutral equilibrium. A body is said to be in neutral equilibrium if it neither returns to its former position nor moves further away when tilted a little. Or the equilibrium if that body is called neutral equilibrium whose CG is neither raised nor lowered undisturbing. Example: 1 horizontally lying cylinder and funnel, 2 lying a ball on the floor. Center of gravity. Definition: it is the point at which the entire weight of the body is said to be situated. Or the point on a body at which the whole weight of the body appears to act. It may be on the body or outside the body in case of a hollow object. 1 shape. Uniform rod shape of gravity. Center of rod. 2 shape. Circular plate shape of gravity. Center of the plate. 3 shape. Square shape of gravity. Intersection of diagonals. 4 shape. Rectangular shape of gravity. Intersection of diagonals. 5 1 shape. I-am shape of gravity. Intersection of diagonals. 6 shape. Triangular shape of gravity. Intersection of diagonals. 7 shape. Sphere shape of gravity. Center of the sphere. 8 1 shape. Cylinder shape of gravity. Midpoint of axis. Center of gravity of a regular body. Suppose we want to find the CG of an irregular shaped metallic plate as shown in the figure method. Drill few small holes near the edge of the plate using hole A. Suspend the plate from a nail fixed horizontally in wall. Suspend a plumb line from the supporting point of nail. When the plate and plumb line will come to rest position, draw a line A on the plate along the plumb line. The center of gravity is located somewhere on the line. Repeat the above procedure using the holes B, C, and D. The lines AA, BB, CC and DD intersect at point G, which is the common point to all these lines. Result: therefore point G is the center of gravity of the plate.